So I'm here to talk about writing real-time applications for Linux, because this is not obvious, and we need to spread a lot of awareness. The company I work for, Linutronix, I'm one of the happy hackers at Linutronix. We're currently working on documenting all of this stuff that we've been working on for 20 years. Hopefully this time next year, there will be official kernel documentation where it's all documented. Right now, all you have is YouTube videos and blog posts and social and things like that. So it's, yeah. So we're just trying to spread a lot of awareness. So I'm going to start off with a bold statement. Linux can do hard real-time. Yes, I did say this. And to qualify this, what do I mean by hard real-time? I mean that if you miss a deadline in your application, it's a critical fail. Your system has failed. And it could be catastrophic. So this is how we define the preempt RT developers. This is how we define preempt RT. So if you miss one of your deadlines, it's either a kernel bug or more likely it's a problem in your application design or implementation, right? So you should never, ever, ever miss your deadlines with preempt RT. And since 6.12, it is mainline, so you can just turn it on, which is an amazing thing. It's about 25 years in the making. And actually, Thomas Gleixner wrote a book, a very mini book about it, that talks about the whole history of the last 25 years. On the table upstairs, there's a whole stack of these. It's all the rest that we have printed. So if you're interested in kind of reading a very technically accurate and interesting look back on 25 years, feel free to grab one. There's not a whole lot left, but maybe you're interested. Okay, so we had this huge celebration. This was like last September. And for us that have been working on this for 20 years, 25 years, it was a big celebration because we'd worked a long time to do this. But the rest of the world was like, yay, is this good? What happens? What does this mean for us? Do we have now a deterministic Firefox with guaranteed latencies? Like, what does this mean? And no, it does not mean this, because Linux is still a general purpose operating system. And when you turn on preempt RT, you still have a general purpose operating system. So actually, if you turn on preempt RT or install a preempt RT kernel, you probably won't notice anything different on your system, because your applications are doing the same thing that they were doing with a non-preempt RT kernel. And the applications are the things that have to do the magic. Of course, with preempt RT, what you get is a new set of semantics to certain functions that make it possible to do hard real-time. But the applications need to do that, and that's why I'm having this talk. So this is basically the main 6 things you have to pay attention to when you say, okay, I want to do a hard real-time system or application or whatever. What are the things I need to be aware of about Linux? So let's just go through these. So the first thing is we need our application to be in physical memory, and all the libraries we're using and all these things need to be in physical RAM, obviously. If they're not in physical RAM, then it causes a page fault when the CPU goes to these instructions or we start accessing this memory or whatever. We get a page fault, and Linux has to scramble to get memory, and this is fatal for all real-time applications. So we need to make sure that our application is always in physical RAM. So what are the things I have to worry about there? First of all, you have to realize that Linux maps memory on demand, right? So allocating memory is really fast because you haven't allocated anything yet. It's just marked, you've allocated this, but you haven't actually. When you start touching that memory, that causes page faults, and then you start getting 4K, about 4K a piece, you start getting that memory, and it's dynamically being assigned to you. So, you know, if I allocate this 2 gigabyte array, that's really fast. But if I start touching this array, you're going to notice that just touching that memory the first time is extremely expensive, right? So you have to be aware of that, this on demand. And it's not just for heaps. It's also for your stacks. The first time my stack grows above a certain page denominator, then I get another page fault, and another page is assigned to my stack. Even the text and data segments of my application. Linux does not load an entire application into physical RAM. It just loads the pieces you're using. And as the CPU moves to new text segments, that'll cause a fault, and it will load that into memory, right? So these things are all loaded on demand. You need to be aware of that because that's all fatal for real-time applications. You have to also be aware that Linux recycles memory. So we're all aware of swapping to disk. You know, if memory starts to get full, then it'll start swapping unused pages to disk. And even if you say, yeah, but I have an embedded system, I don't use swap files, you are still vulnerable to this, because if things get really tight, Linux will start dumping any pages that it can reclaim from the disk, including, for example, the text segments for your application, right? So it's like, okay, I'm getting really full of memory, but if I throw out these text segments, I know that when the CPU needs that function again, I can just repage it from the disk, right? So even on an embedded system with no swap file, you need to be aware that this paging can happen. And then, of course, the glibc likes to reclaim unused heap space. So if I have a huge heap and I'm not using the top parts of it, glibc will actually give it back to the kernel to use, right? So maybe I had all these page faults and got all this memory, and then I wasn't using that memory for a while, and now it went back to the kernel. So if I want to get it again, I'm going to have to page fault it again, right? So these are things I have to be aware of. They're all not good, absolutely forbidden for real-time applications, and there are solutions for that. For example, locking your memory, pre-faulting your memory, and tuning your glibc with mallopt so that, for example, you only have one heap and you're using a true heap. Yes, you're not using mmaps for your heaps. You actually are using, with the break system call, you're actually managing a heap like we all learned in the university. And you can also do things like tuning how your stacks work, avoiding allocating with mmap altogether, and things like this, right? So these are things you can do. I'm not going into the details of these things. You can find them in the internet by Google searching, or I have a talk called Checklist that actually goes into more details. So just so that you know that these are like the key terms to do that, but you need to do that. Every real-time application must do these things to avoid these problems. The next thing is to understand that there are real-time policies and priorities. These are not specific to preempt RT, but with preempt RT, they become really important because they can actually be used much more effectively, because preempt RT is much more interruptible. I think everyone knows this. You have the policies sched FIFO and sched round robin. Basically, it means your application stays on the CPU as long as it wants, until it says, okay, I'm done with the CPU, right? So it's not like the EVDF and stuff where we have certain time slices, our time slices up and we get kicked off the CPU. This doesn't happen with the real-time policies. You stay on that CPU as long as you want. If you go into a busy loop of nothing, that CPU is basically gone because it's just going to busy loop forever. There are different priorities. So we've got from 1 to 99, we've got the different priorities that are available. So this makes it possible so that we can have tasks that are more important than other ones, of course. And the way that this sched FIFO works here, let me get my mouse pointer. The way this sched FIFO works is that if a higher priority task becomes runnable, it has something to do, then obviously it will take over, right? So it's just, if nobody more important than me has something to do, then I can just go all day with sched FIFO. As soon as another task with more priority wants to come in, it immediately takes over, and it can go as long as it wants. There's also this sched round robin variant. This is just, the only difference between those two is if the priorities are the same, then there are time slices between those tasks. So you can actually choose to have two tasks with the same priority kind of take turns on the CPU. But it's only if they're the same. If they're different, it's exactly the same as sched FIFO. Down here, I show you the CHRT tool. This is a tool where you can change the policies and the priorities of running applications, running threads, individual threads. So these scheduling policies and priorities are per thread, right? So you can have certain threads that are real-time priority and the other ones that are just sched other. So with CHRT, you can control that. Or if you want your application to do it itself, you've got sched set scheduler. And there's also a pthread variant if you want to use that. Synchronizing and notification. This is something that you do all the time because we have some sort of protected resource, and usually you'll have high priority tasks that need to modify or read this resource and low priority tasks that need to modify it, and maybe sched other tasks that need to look at it. So we need some way of synchronizing this data and be able to notify each other when this data is changed. For this, you definitely want to use locking, right? We want to protect it, we want to synchronize it, and the pthread mutex type is the type you want to use to protect this. This is the only data type that supports priority inheritance. What priority inheritance means is if I'm a low priority task and I take that mutex, and now a high priority task comes in and says, I want that mutex, then what will happen is that low priority task will get boosted to the same priority level as the high priority task so that it can finish its work and release that mutex, and then the high priority task can take over. And this is really important to avoid priority inversion. We don't want our high priority tasks waiting on low priority tasks. So we can boost them to our priority, they finish what they're doing, release that mutex, and now we can take over. And the pthread mutex type is the only type that supports this. So you need to use this type for locking. Unfortunately, it's not the default that it has this priority boosting feature, so you actually have to turn this on there's a mutex protocol attribute, you actually have to turn on the priority inheritance. If you want to do some sort of notification, often this is so in real-time applications where you're waiting for an event, and as soon as you wake up, the first thing you want to do is grab a lock and look at what the data is. That's a very common pattern. I'm waiting, someone's modifying data, and then I wake up, and then I want to look at the data. So basically, you've got a conditional variable, an event, a wait object, and we have a mutex, because we need to get to that data, which will also be protected. This is what conditional variables are. They basically marry a mutex to a wait object, so that you can have a nice, clean handover when someone's modifying the data and they wake me up, and then I will wake up, grab that mutex, and look at that data. That's exactly the pattern that conditional variables are for. It's safe to use the glibc implementation of convars. However, you might be also interested in librtpi, which is also in Debian, which has a more efficient ownership transfer. So basically, I've modified the data, and I want to wake someone else and say, hey, look in there. Basically, a more efficient transfer of the mutex to say, okay, now you have that mutex, and you can look at the data. So it's a little bit more efficient. With conditional variables in glibc, it's okay, but if you've got a lot of contention, it's not super efficient, but it'll still be correct. Cyclic tasks are something we have all the time. Maybe once every millisecond, we have to read some sensors or check some registers or do some sort of work, whatever we need to do. This is actually quite often in real time. You need to be aware that there are APIs, system calls, that are not RT safe. For example, timerfd is a big one. Everyone thinks timerfd is great. It is great, but for preempt RT, it is not great. The problem is that depending on when the timer interrupt fires and the current load of interrupts on the system, that interrupt handling might actually get deferred into the ksoft IRQ daemon, which is running as sched other, which means your high priority task, which is waiting for wake-ups every millisecond, that might get the responsibility of that wake-up might move into a sched other task, the ksoft IRQ daemon, which is fatal, because sched other it'll be scheduled when all the real-time stuff is done. So timerfd is unfortunately not good. I hope someday we can fix timerfd so that it is good, but right now it is not. Also, POSIX timers have the exact same problem. POSIX timers are even worse because you're kind of in a user space interrupt context when you come in user space, so you're not allowed to take mutexes, you're not allowed to do a lot of things in an interrupt handler. I think yesterday there was some talk about signals and how horrible they are. They are horrible. So the POSIX timer interface has this deferred interrupt problem, and it's using signals. It's just ugly, ugly, ugly. So the best thing to do, and the correct thing to do, is really to have a dedicated thread. It's very simple. It just runs a clock nanosleep, so it sleeps amount of time. It'll wake up, does its work, goes back to sleep. So it's a very simple loop of just doing my work, and when I'm done, I go back to sleep. The beauty of this is you have a dedicated thread, so you can give it a dedicated policy, a dedicated priority. It's a normal thread context, so you could take mutexes and do everything you need to do there. You'll have priority boosting and all of the stuff, so you have all the control that you need for this cyclic task. Important here, make sure you're using the monotonic clock, because it's immune to time setting, for example, every year or twice a year when we change our clocks, or for example, with the leap second and things like this. Clock monotonic is immune to these sudden changes. And also absolute time is important because you shouldn't be calculating, okay, I did my work, now how long do I need to sleep? No, use absolute time. So if I know I'm waking up every millisecond, I can calculate my wake-ups for the next million years. It's going to be every millisecond. I can calculate that. And if I'm using clock monotonic and absolute time, I know exactly when I'm waking up for the next million years. So I don't have to calculate anything. I just go back to sleep, and I just had to increment that by 1 millisecond. Just keep incrementing the previous sleep by 1 millisecond, right? And so I have a nice, steady, no variance, no drift, even 1,000 years in the future, I'm still hitting this 1 millisecond as the humans have defined it. Task and interrupt CPU affinities. This is also important because often you want to dedicate certain CPUs for certain tasks. So it's possible, for example, to isolate certain CPUs and say, I'm only going to run my real-time tasks on this CPU. This is, I think this was talked about yesterday in the OSCIL talk, so that you can have less interference from other tasks. There's still issues like caching and things like this that you have to be aware of. These are actually hardware issues. But getting the processes, the different tasks off my CPU so that I can reserve it for real time can be very helpful just to reduce the noise on that CPU. Generally you use CPU set for that, so there's a man page. It's based on C groups, how to use that. There's also the isol CPU's boot argument, which is currently deprecated, but a lot of people are still using it. It's a little bit easier to use, but obviously you don't have the fine control that you have in C groups. Again, here you see the API of, if I want to manually set the affinities, I can use the task set tool, so I can manually set affinities per thread, right? So I can say this thread is pinned to this CPU, the other threads are not on that CPU, or whatever. However I want to set that, I can do this per thread, I can set these affinities. I can also do it as a program with the sched set affinity. You can also use C groups, which is basically what's set up here. So you can use C groups to basically confine applications or a set of applications to certain CPUs. And you can also set the IRQ routing for the physical IRQs. So for example, I can say that my network IRQs should be firing on CPU 3 because that's where I have my real-time application, all these things. I want the IRQs to be firing on the CPU that's going to be dealing with those interrupts. So I don't have to do any IPIs, the interrupt fires here, and now I have to do a wake up on another CPU. That costs time, and we don't have to do that, right? So you can actually control the routing of your IRQs so that the hardware is really from the moment of interrupt doing what you want it to do. The last topic is real-time networking, and this is something that's actually quite tricky. The first thing you need to have is hardware that will support real-time networking. So you don't have to have hardware that supports real-time networking because you can emulate all this. But if we're talking about real-time, then we're talking about being serious, and we're going to buy the hardware to do serious real-time networking. So for example, we need to have the ability to do precision timestamps in the hardware. We need the ability to specify priority traffic classes and time-aware traffic shaping. We need to be able to send packets at exactly nanosecond specified times is when we want to send them on the network. And this multi-queue allows us to actually identify when traffic is coming in on these different traffic classes. We can say, okay, this high priority, this is going to go to CPU 4, and it's going to be handled CPU. The stuff that's not important is going to go to CPU 2, right? Like we can actually, the hardware can do this, can actually route the incoming traffic. So these things are very important to allow you to do real-time networking. Now currently, you also have to have an isolated CPU for your real-time networking. So I can't just do normal networking like I'm used to. I actually have to decide, okay, I have a CPU for it. I'm going to put the hardware interrupt on that. I'm going to put the interrupt handling thread on there. I'm going to put the NAPI instance K thread on there. And my application my real-time application is going to be in there. So basically, I have a dedicated CPU that's just doing real-time networking. That's how you have to do it right now. But actually, there are patches currently on the Linux kernel mailing list so that we don't have to have that requirement, right? So it would be nice if they could, all these things could just be on whatever CPU is nice, because then allowing things to just run on all the CPUs, you're just giving the scheduler the freedom to schedule good. So forcing the scheduler to always use certain CPUs is not always the most efficient approach. Excuse me. So those patches are currently on LKML, and hopefully with like 6.16, 6.17, this requirement will no longer be there. There's also a tool called RTC Test Bench. This is a tool that is basically, it's a collaboration of all the hardware vendors of this real-time networking hardware because they wanted to have some tool to verify that this is actually working correct. This multi-queues are working correct, the non-real-time traffic and the real-time traffic are being sorted correctly, that we want to measure exact timing and latencies of everything. They wanted to have a tool for this, of course. And Linutronix developed this tool. We're the maintainers of this tool, but it's a collaboration effort of all the hardware companies. And so you see it's a real-time and non-real-time traffic validation tool for converged Ethernet networks with and without utilization of TSN mechanisms, right? So this is the tool. If you want to do real-time networking, that's the tool you need to go to test. Before you start writing applications, test your hardware. Can we do real-time networking on this hardware? Because if you can't get it to work on that, you will not get it to work with your application. So this is a quite an important tool because real-time networking is complicated. And the nice thing is it has a lot of pre-existing configurations, so you can just kind of take things out of the box and configure it fairly easily. Okay, so we've heard about all these things that are there that we have to be aware of. What are some design considerations now when we're doing our application? The design. The first thing is you need to understand this idea of event flows. A hardware interrupt happens. This is going to go to an interrupt handling thread on PreemptRT. That's going to wake some sort of application. This application might wake another application. So there's going to be like a chain of events of the flow. And this flow should go from high priority to low priority. You shouldn't be having low priority tasks notifying high priority tasks because this is kind of a mistake in your logic. Really, the events that come in need to be high priority, and then you can sort them out and say, okay, yeah, that's not so important. But if they start out as low priority, they may never get scheduled to come to high priority. So you really have to make sure that the direction of priorities in the event chain is always going the same or going down. This is really important. And obviously, the hardware interrupt, this is what you'd consider the highest priority. Yeah, this is basically all events originate at some point from a hardware interrupt, right? Software just doesn't magically do stuff. There's always some sort of hardware event that happens that triggers that chain. Real-time work. Only use the real-time priorities for actual real-time work. So I've written in my documentation, my requirements documentation, we have latency requirements. We have to fulfill these deadlines. That's the work I should be doing in real-time priority. Nothing else. No pthread joins, no let's read some configuration files. Don't do this stuff in PreemptRT. I'm sorry, not with PreemptRT, with the RT priorities and policies, because what you're doing is, it's not that it's in and itself is bad, but you're taking the CPU from maybe other important tasks on the system, right? If I'm using a real-time priority to do a pthread join, this CPU cycles I'm getting maybe could have been going to an important sched other tasks. Sched other tasks do have important jobs too. So really keep yourself at sched other. There's enough tools available with NICE, with C groups, and all these things that you can actually tune your system how you want without using real-time priorities. I've seen people use real-time priorities because they're like, yeah, I want my web browser to get a little bit more CPU cycles. No. If there is no deadline specification, don't use real-time policies and priorities. It's that simple, right? As soon as you see someone using a real-time policy, then you can immediately ask, can you show me the specification for the deadline, right? I want to see it. What is it, 100 milliseconds, 100 microseconds? Where is it? We have to write this down because we're using real-time stuff here. Okay, and then the last thing really to consider, when a real-time application goes to sleep, this is kind of a scary thing, right? I have a real-time application or a task, and I'm going to sleep, right? It's like I have a huge test in the next morning, and now I'm going to bed. That alarm clock better wake me up, right? Like I'm going to sleep now. And this is the same thing with the real-time tasks. You really have to ask yourself, who is the waker? Who is going to wake this task in all scenarios? Because you need to make sure that that waker is at least as important as I am, right? When I go to bed and I have that big test the next day, that alarm clock is more important than me when I go to sleep because that thing needs to wake me up, right? So really in all scenarios, you need to consider who is going to wake this task up. Yeah, when I do a clock nanosleep, it's the hardware interrupt that's actually going to do the waking, right? I can rely on that. Okay, so we have all this stuff that we've seen, so now we can go out and we can write perfect real-time applications, right? Wrong. You will not do it correctly, right? And the reason why you still will make mistakes is because Linux provides many, many interfaces, and you don't know the details of how it's implemented. You don't know if it's RT safe. For example, timer FD. A lot of people are shocked to hear that they're not supposed to be using timer FD. It's not their fault, right? But it's just the fact. They can't use that, right? So people are going to use interfaces that are wrong. Also, not all subsystems and drivers are doing things the same. So if I'm using like the GPIO subsystem, it might be okay to read some GPIOs, but if I'm using the I2C subsystem, it might not be okay to communicate with an I2C controller. It depends on how the subsystems and the drivers have implemented that, right? So you can't really know. Also, the libraries themselves might be doing things wrong. Even the libc might be doing things that are not RT safe, right? So you have all these problems that you don't even know. And also, the first 10 slides I showed, that was a lot of stuff, right? So you're supposed to keep all of this in mind, and now you're going to do a big application. You're going to mess it up. And so this is why we decided we wanted to have a tool to show us what we're doing wrong. And just recently, so the 12th of May, from my colleague Nam, we posted the runtime verification monitor for real-time applications, right? So it's currently in version 8. We think this is the version that will get accepted. When you've applied these patches, you'll see in the kernel configuration you have an RT app monitor. This monitors your entire system to see if any real-time applications are causing page faults or they're sleeping incorrectly, right? They're sleeping in a way they shouldn't be sleeping. And basically, with these two scenarios, if you can catch that they're going to sleep incorrectly or they're being woken up incorrectly, that's the opposite of sleep, right? Or they're causing page faults, you've covered a whole bunch of problems. So what this is just a nice tool that you just turn on. And so the way it works, if you have a system patch like my system here, basically you just have to turn on the RT app monitor. A reactor is, there's different ways to react to when a problem is found. So one of the options is to panic the system. So you could actually say panic, so that if I have a page fault in a real-time task, the system panics, for example. In this case, I'm just using print K, right? So it's just going to let me know. And then you can use perf to just record, and you have these two events, the RV error sleep and the RV error page fault, that you're just recording. And if I'm saying -G, I can also grab the user space stacks. So after I've done some recording, I've just let this run on my system. I'm watching YouTube videos, I'm doing Zoom, whatever I'm doing. And then I can break perf record and take a look at what it found, right? And I see full back traces of things that were incorrect. So but it's only for real-time applications, right? These are real-time applications. So we're saying that, for example, PipeWire, which is a very important real-time application, is supposed to be replacing Jack, which is a professional audio solution. And we see that some warnings appear there. And in this case, we can see that actually it's doing an epoll wait. And unfortunately, epoll is currently also a function that's not RT safe. So I can look in there, and now I can look in the PipeWire code. And we actually did this. So we looked into the PipeWire code. And my colleague Nam actually created a merge request telling him that it needs to be changed. We need to get away from epoll. This is the problem. And here are the patch to do it, right? So we could fix it. Now, there's a lot of epoll in PipeWire. So there's a lot of things. So it's going to be things that we're going to have to do one at a time. But this is something we did. And if you look, what is the actual problem here? When you look at the code, basically what's changing is this is the interesting part we're removing. What PipeWire was doing is it was telling the real-time task to connect nodes, right? So if you have your PipeWire and you're connecting your speaker to your microphone or something like this, you're creating a node connection. And there's no reason for that to be done in real-time context. But PipeWire does it in real-time context. It basically does this PW loop invoke, which basically just tells the real-time loop, hey, can you create this connection for me? Which is it's just wrong. It's just wrong because it has nothing to do with real-time. You should not be doing the real-time task. It was a pure convenience thing that we implemented that way. So basically what this patch did, and the patch is bigger than this, but basically it added a mutex lock with priority inheritance, and we're protecting that list with that lock. And when the nodes need to be connected, I just do it in the sched other context, right? And I just take the mutex lock, I connect those nodes, and release the lock. I don't have to have a real-time task do it for me. And when the real-time task wants to look at these node connections, it also needs to take the lock. And if my sched other is holding that lock, it'll get boosted, make the connection, get deboosted, and now the real-time task can use that list. Right? So it's a relatively conceptually simple change, but it's just, again, showing real-time tasks should only be doing real-time stuff. Now, as with all maintainers, the patch wasn't good enough how it was, but he took it seriously, so he actually, in the PipeWire, there is actually a loop lock branch that's been created, and so you see that Wim actually, he did his own version of that. That's fine. He's the maintainer, so he sees, okay, we should do it a little bit differently. So you can actually see these 6 patches that he put on there that basically implement that. So he's actually seriously looking at this. He didn't even know that priority inheritance existed and things like this, right? So, we had to give him a little lesson about how it works. And he's like, okay, yeah, now I understand. Now I understand what I have to change and why. Unfortunately, that was just one thing we found wrong with PipeWire. PipeWire has all kinds of things. We saw page faults happening in real-time context. It uses timer FD for a lot of stuff. So PipeWire, which is supposed to be this amazing real-time application, and it does a good job, but it's not ready for preempt RT. Like, it's not doing things the way preempt RT needs it to do, right? So these are just little things, but the nice thing is we have this tool now that we can just run. You just turn it on and just do whatever you do on your system, and it's just going to start noticing the real-time applications that are doing something they shouldn't. Now, that doesn't mean that everything it finds is an error, right? Sometimes it's like a false positive, like ePoll is not always bad. There are situations where it's okay to use ePoll. There are situations where it might be okay for a low-priority task to notify a high-priority task, right? There might be some, but generally speaking, you're doing something wrong. So you have to go through on a case-by-case basis and say, like, is that right or is that not right? But it's a good start, because this is the first time that we have something that just kind of spits out. Because until now, customers had to wait till their device blows up, and then they have to reproduce it, and then they have to like trace it and use Perfetto and all this stuff to try to figure out what went wrong. And now we have something that maybe it can just immediately tell you, hey, you have priority inversion because this low priority task is waking you, right? So these are things that can really help there. So that's the end. So it's not perfect, but we're working on it. We're working on the documentation, and I hope by having documentation, people can read about what's correct and what's not correct. By having this RT monitor, they can just turn something on, and it'll just start complaining about the real-time application. We hope that this will try to educate people and get them to better understand how to use preempt RT correctly so that they can really have hard real-time with Linux. Any questions?
How do you work around the power usage cost of using a small sleep to implement your timers?
I'm not sure what you mean using clock nanosleep or?
Yeah, so something has been chased in desktop world for years now. It's the recurrent wake up of CPU. So basically every 20 milliseconds you wake up the CPU, every 5 milliseconds. Yeah. Do you have a technique where you can sleep longer but still have a chance to change your deadline later because you have some other information that maybe your deadline is shorter, so you don't want a big sleep, but you don't want a small sleep because you don't want to keep waking up?
Yeah, I mean, this is a really complicated thing, and these are one of the things where power management is a direct enemy to real time, right? So I'm not aware of any interfaces, if I understood you correctly, so that I can push out my delays further if I don't want to wake up. I mean, there's modes like no hertz full, where it just won't wake up the system at all, but if I do like a clock nanosleep, I'm actually setting a timer. That will actually wake me up. So, but if you just want to avoid the tick, there is the no hertz full that will completely get rid of the tick, and you're only going to wake up when actual interrupts fire, right? So you can turn that off, that tick. But you have to be aware that the tick is sometimes important because it's in charge of updating the clock diffs. So one of the problems is that when you do wake up, like for example, when a really important interrupt happens, the kernel will first update the clocks because it hasn't done that for maybe 2 months, right? Because it's been sleeping. Right. So the problem is with no hertz full, we usually recommend against that for real time. because you're delaying work to the moment when you have to do something else, right? And because you'll wake up for something important, and now I have to do all this work I didn't do because I was sleeping, right?
Yeah, so basically that's where my question was going. Basically, do you have any strategies where you would do something less real-time to wake up earlier, and then you go more real-time to get more precision or something? Is it something you've ever done? Or?
I see what you're saying.
Because power management is going to be a real challenge for PipeWire, because it's not meant just for like a wired device. It's also for your laptop, for your phone. And
Well, sure, but I mean, the principles are the same. When I stop having my real-time task do non-real-time stuff, that's not a bad design decision. Actually, when he started looking at this, he's like, oh, actually, this is a better design when we start decoupling real-time for the real-time stuff. So there's nothing wrong with making Firefox real-time capable. It's not going to make Firefox bad, if that's even possible to make the Firefox real-time capable, or even what that even means. But yeah, so generally, it's not a bad design decision. When I write just regular code, I'm used to writing real-time applications. So even if I'm just writing some stupid hello world, I'm writing it to be RT safe because I'm just used to that. And when you get used to it, it's actually quite easy. Right? There's just things I don't use signals, I don't use timer FD, I can use other things. So, yeah.
Thank you.
Yeah.
Hey, so you mentioned that you implemented support for PipeWire and PreemptRT. Do you have any figures for the round trip latency?
I'm sorry, the question, what was the question part?
Metrics for round trip latency tests.
For network.
PipeWire.
Going through PipeWire.
You mentioned
So you're
PipeWire.
just talking about locally, right? You're not talking about network or anything like that?
No, we're talking about PipeWire and audio playing.
Yeah.
And you mentioned in real-time support, and you had to implement some
Yeah, so we
changes.
didn't do any testing to see latency because maybe at some point we will, I don't know. We didn't want to become maintainers of PipeWire. But we're just noticing like design patterns that are wrong.
Okay,
So we're just helping them fix that. That should improve latency in bad scenarios, right? Like if there's never mutex conditions, if I'm not getting cache misses, all these things, then I can have a bad design work great. The problem is when we get memory pressure and we get only cache misses and all these things happen, memory bus contention, then all of a sudden things just explode, right? And that's where the design makes the difference.
Right,
so we're catching things that are badly designed, but it hasn't necessarily, a bad thing has not necessarily happened.
Yeah, so it makes sense because years ago we implemented Xenomai support as a plugin in PipeWire, and we were measuring 8 milliseconds round trips. So obviously we didn't notice these things that you mentioned, so it's a matter of testing again and see if we see an improvement.
And you should definitely do that to make sure nothing gets worse.
Absolutely.
Right, like making these fundamental changes in the design and we see PipeWire gets way worse. That's not good either. Right. So.
Yeah, leaving the deeply technical parts for a little bit, we all know that we also need to talk to people who are not understanding all of this stuff, like your Firefox users. What's your punchline to tell people enabling PreemptRT on a box standard system will actually not make it faster, but slower? Because I have to explain that every time.
Yes, this is important to understand that real time is not as fast as possible, it's as fast as specified, right? So PreemptRT does a lot more accounting, has a lot more interruptibility, and you don't just get this for free. We had to write a lot of code to do this. So the CPU does a lot more in PreemptRT. So just turning it on for fun, you're going to give your CPU more work, and you're not necessarily going to see anything better because the applications are not written for PreemptRT, right? Like I mentioned. So it'll work the same as before, but the CPU has a lot more work for nothing, right? So really, PreemptRT should be reserved for real-time loads. We actually do something real-time. We're going to do this extra CPU work and accounting because we get something for it. Our applications can take advantage of it, right? So it's more work for the CPU.
Could you go back to the PipeWire code example, that with the log and the loop?
Oh, here, yeah.
Yeah, so when you move that out and have a log, it doesn't improve the worst case, right? It's because in the worst case, you are just taken the lock, and then the real-time task has been woken up, and then it needs to wait, and you have this random time that you need to wait. So this doesn't improve the worst case, right?
Exactly, and this is what Wim at first talked about. He's like, yeah, but in the worst case, we still have to wait for the list to be updated before I can do the real-time stuff. We're like, yeah, but you have to do that now, because you're posting something on the real-time loop. It has to update the list before it even considers the next event. So it's not better or worse than the worst case. It's the same. But the difference is that if we're not in this worst case scenario, then we don't have to be in real-time context to update these lists. So the normal case has been improved, and the worst case maybe is the same, but the normal case has been dramatically improved, right? And that's really the goal. Don't do RT stuff if you're not actually doing RT CPU instructions, right?
Okay, thank you.
Thanks for good talk. I would like to add one small comment to the first one about power management. For example, you are talking about tasks which could be related to hardware, and you told about RQ affinity and other things. The same applies to power management queues, right? That when some drivers, for example, UART, could go and on the sleeping CPU, you need to wake up, and you cannot provide time-based protocols. So you need also to set up not only RQ affinity, but PMQOs. And what I noticed that many even experienced developer doesn't know that, like you said, in general purpose operating system, with all gigahertz of CPU, UART is a hard thing. The CPU cannot afford it, actually. Cannot do UART nowadays. And one question, have you already answered with PipeWire? It's like the application which needs to be real time. But the other half of the question is, what applications currently already implemented as a real time, and what applications that will never need those? Like Firefox, does it need or not? Or?
I mean, the applications that don't need real time is probably most. I mean, real time is a pretty special thing. It's usually you don't have such timing requirements. But there are applications that do things correctly. I mean, the RTC test bench, for example. We ran this tool on the RT test bench doing real-time networking, and it said nothing. It found nothing. And Kurt, also a colleague of mine, he celebrates it. Yes, I did it right. Okay. There are applications that are doing it right. So, but most don't. And to your first comment, power management is extremely complicated. And when you're doing real-time and mixing power management, you're opening a can of worms. Yeah, so generally speaking, if you're going to be doing real-time, you need to forget about power management. That's currently the state today because power management is so complicated. And as soon as you start ramping down hardware and putting hardware to sleep, you can seriously be jeopardizing your real-time requirements. So it's really, really scary to play with those. So, I mean, of course, if you have people that are really skilled and you have all your tests and everything, it's certainly possible. But it's a lot of knobs and switches to play with to get it right.
So if I have a customer that is doing their application and I'm developing the BSP and they're like, oh, we want it to be real time. And I'm saying, okay, then you have to change the code. Then they say, nah, we don't want that, but we want it to be real time. What are my options then? Can I tune these things? Like, I know certain things don't do time FD, that's hard to do, but malloc and of course the real-time priorities we can change from the outside.
I mean, this is also something that the RT monitor could be helpful because they say, let's just make it real time. Make it real time, turn on the RT monitor, and then give them the 50 pages of back traces that say, this is stuff we're doing wrong. It's actually a problem for real time. So you actually have something in your hand where you can say, this application needs to be changed, and here's all the points where we have to do it, right? But you have to change it because if you have priority inversion, if I'm blocking on my high priority task is blocking on a mutex that's owned by low priority, and I don't have priority boosting turned on, I don't have real time. It's just sitting there, and this sched other might be preempted, and it's not going to get scheduled for another 10 minutes. And the real-time task is like, I want to deploy the airbag. Sorry, you can't, right? So it has to be taken seriously.
More than 10 years ago, I had a problem that the non-real-time threads were interfering with the real-time threads due to page locks. Is that something that still exists, you think? So the solution back then was to just make sure that non-real-time is in a separate process and not in the same process?
Just to understand, you're saying the non-real-time tasks were interfering with the real-time tasks.
So concretely, it was a non-real-time task doing a fork, and because of that, there was a page lock taken on many pages. One of the pages was actually used by a real-time thread, and that caused issues.
Yeah, so this could be really bad. If you've had forks and now we have copy on write pages and things like this, these are things you have to be aware of with your real-time application, right? So if the application is doing any forking, and that's also going to be a real-time application even later, you need to be aware that you have pages that are copy on write. So yeah,
so it's still a good idea to keep
it's a good idea to keep them separate
in a separate process.
Yeah, it gets really tricky when you mix real-time and non-real-time in the same memory space. You can do it, but it's tricky.
Real-time and dynamically loadable module libraries. Is there something to do there? Because there's the resolution of symbols in the dynamically linked libraries that happen lazily, usually. So you should turn on RTLD now, so that that's just like doing mloc all. So you have to resolve all the symbols at the time of loading the library and not wait until you get to do it lazily, because it takes more time.
Correct. Those are some of the tricks you have to do, and I didn't go too deep. I have another talk on it's called the real-time checklist or something, where I go a little bit deeper and talk about these things like immediate binding. It's important because that's not necessarily related to memory. It's just the dynamic loader is being lazy and it's waiting until the wrong moment. I actually want to use the function, and now it's actually going to set up the jump. That's bad for real time. So there is a lot of little things, although that's not that expensive. Because you have to keep in mind that with preempt RT, generally you have to be expecting, depends on your hardware and what you're doing, but generally you need to expect 10 to, let's say, worst case on cheap hardware, maybe 150 or 180 microseconds. So this is the kind of latency that will be there. So if I have a real-time application that has requirements under 100 microseconds for jitter, then I need to be really careful what hardware I select, right? I can't just take some Raspberry Pi off the shelf and expect to get 40 microsecond worst case latency. You're not going to get it, because the hardware just it's not set up for that. So just have to be aware. We're kind of talking like, I always tell people about 100 microsecond world. That's about the latency world we're in. If you have requirements less than that, you need to really be careful of your hardware as well. The hardware plays an important role. Memory, bus, latency, and stuff like this, contention.
All right. My question is preempt RT capable of hard real-time? And if not, why?
It is. That's my first slide. Where are you? All right. Do I see you? It is, because people are doing it. And it's not just since September. People have been doing it for 20 years, right? People are flying to the moon and going to Mars and doing things with preempt RT. And they're actually, especially if you go like USA and you see like autonomous cars everywhere, this is Linux everywhere and preempt RT that's handling a lot of these things. So it is there, but you have to program your applications correctly, right? And that's the big hook, right? You have to write your applications correctly because it's a general purpose operating system and it has so many things. Maybe someday Linux will be so far that you can use any interface, any driver, and you'll be RT safe. Maybe someday we'll get there in 20, 30 years. But right now, it's not that far. So you really have to be careful. What system calls am I using? What arguments am I using in these system calls? It's important. So right now, we just want to document these things, and hopefully the document of exceptions will get smaller over time, that you can use epoll, you can use timer FD, right? We want that. But right now, you can't. So.
Thank you. One last question.
Thank you for the talk. I had one question on the RT monitor, like how exactly it finds the fault in the application that it's not real time? Does it have some logic to check if high priority task is not getting the CPU or some tolerances there, and how accurate it is?
Yeah, I can actually just really quick, we're kind of late on timing, but let me just really quickly just show you actually. Put this in the background. I kind of, oops, LTL. So actually the way it works is it uses linear temporal logic. So all of these monitors are implemented using a state machine. So basically you have a kind of an abstract logic that describes the state machine, and the state machine, basically if you violate the state machine, that's when the errors come. Now the state machine that was implemented in the runtime verification code was very primitive, and it just wasn't powerful enough to express the kinds of things we want to express. So NAM actually implemented a linear temporal logic models, and this is what that language looks like. So you can see things that we're defining things like RT-friendly sleep, RT-valid sleep reason, RT-friendly nanosleep, right? So that we're defining these things, and then at the top is just a simple rule, right? So we're just setting a rule that if you're an RT task and you go to sleep, then it needs to be either an RT-friendly sleep or it needs to be on the allow list. So there's a few things that we just allow always. And just setting up these rules, I mean, you can see things, for example, an RT-friendly wake, things like woken up by equal or higher priority, right? So we kind of define that event, and this is actually implemented in the kernel. There's actually a point, it's sched switch, or I'm sorry, it's sched wake up, where we compare the priorities. And if it's a real-time task, we compare the priorities, and we can see if this event is true or false, right? So we can use these general rules, and this is turned automatically into kernel code and then built into the kernel, right? So it's in the kernel that I'm running right now. But it's just based on rules. So these rules will start to get more complicated as we start finding more things and more exceptions and things we need to improve. But it's a very high-level state machine. Yeah.
So you don't have to give any parameters to the tool, just run it?
No,
okay.
You just run it. Like it's literally, that slide I showed you, echo 1 into that thing, it's running. And then just check your D message if you turn on the print K, or you could turn on the panic reactor, and then your system will just crash if anything goes wrong, right? But that's pretty hardcore. But I hope that someday we get to the point where you can do that. We're not triggering any false positives. So.
All right, thank you, John. That was wonderful.